So, hello together to our last lecture this semester in statistics, and we will do the last exercise, and afterwards we will talk about the exam. So, let's start with the exercise. So, we have a little time series, and we should apply our different forecast method, and therefore we just take our data and put this data in an Excel sheet. Well, on this you have quite often if you want to get data from the net or from some PDF paper into your program that you cannot get this data directly, and for this you should know how to change the format of your data that you can work with it, because now you have all the data in one column, but here you have the possibility that you can, where is it? Oops. Change the data a little bit here, and then you need to see here with the spare part, and here you see downwards that then the data is sorted into two columns. And now we can use the data. Okay, what shall we do? First task, moving average with 3 and 5 months. What do we have to do then with our data? Can you give me a hint? Well, moving average we apply because quite often our time series have some outliers, and in order to smooth these outliers we just average our data for some period, and here we should average our data for 3 periods, for 3 months, for 3 quarters, sorry, 3 quarters we need here. So we just take the average of 39, 42 and 103 and then move this then 1 quarter forward. So equals the average up of our 3 quarters. Then we have here the average of 39, 42 and 103, and if we copy this data 1 forward, then 81 is just the average of 42, 103 and 98, and moving forward we then obtain all our moving averages and well, if we would apply now our formula in this cell, then of course this cell is missing, and let's have a look into our formula for forecasting with a moving average. Then this means we take the next data point using this formula and y hat t minus t plus 1 means then here inserting in our case 1 over 3. So this would be then in our case, let's have a look, 23 Q1 we need. Y hat 23 Q1, then 1 over 3 plus and then we have here the last one, y of 2022 Q4 plus y 2022 to 3 plus y 2022 Q2. And going back to Excel, for 2023 Q1 would be then the average of our three values here. This in red, and this is our forecast. So, and let's also take the first task. So we have moving average 3/4, then y hat 223 q1 equals 606. What else? And 5 months. What would be 5 months? Come in here. Oh, sorry. Let's do this one like this, and the 5Q forecast. Then we need the first 5 values of our data. So from 39 to 167. And then we would end at this point, and our forecast would be the average of the last 5 data points. 3, 4, 5. And this would be 574.6. Y hat 2, 2, 3, Q1, 574.6. So this is 1/3. This, this one is 505,645 and plus 659. And this would be 1/5. These 3 numbers up, up, pick, up. I'm still trying, so let's write it by hand. 1/5. And we start at 587. 587 plus 468, 468 plus 505 plus 745 plus 659. So exponential smoothing, choosing a specific alpha. What was exponential smoothing? There we have this formula. That we start in the beginning with this initial condition. And then we create a new data series, and in the end we use this formula to forecast the next value. So just choose one alpha. What should we use for alpha? Well, then let's try a low and a large value. So alpha equals 0.2, and let's say alpha equals 0.75, so to speak. Then the first value is just our value of our time series. So we obtain here 39, and here also 39. And for the next value, we take the weight, alpha equals 0.2 in the first case, multiplying this with our true data point, and then with alpha 1 minus alpha, the forecasted value. So what we take then is in alpha equals the next data point equals the true data point times 0.2 plus 1 minus 0.2 times our forecasted value. And then moving this down until the end. And in this case, we have to calculate the true data point 39 times 0.75 plus 1 minus 0.75 times the forecasted value. The first one is of course the same as our data point, so nothing changes, but then in the next case we will see our change, and then we have these two as a forecast. and this. So then we have with alpha equals 0.2 that y hat 2023 Q4 Q1. Equals 504.1, 504.1, and for alpha equals 0.75, we have Q1 is roughly 648.2, 648.2. And if we just have a look at the numbers of our time series, why do we have in the case with a high alpha 0.75, if you look at the data, a much higher forecast? What is the reason for this? So actually, what is always a good idea is to look at the data and if you keep in mind this diagram, why would we expect then if we choose a high alpha also a higher number for our forecast? And this is what I mean. One should always know what you are doing. Well, what we see here is that we have an increasing trend, and choosing a high alpha means that we put a high value of on the last data points. And this then means that we have a higher value in our forecast on the last data points, which due to our general trend have larger values, and therefore it is not very surprising that we have here also a higher forecast choosing a high alpha. Okay, what else? Average growth rate, quarterly and yearly, and this we should do also with seasonally adjustment. So let's start with average growth rate quarterly. And what do we have to do then? Oops. Average growth. Well, then we have to calculate every single growth rate from quarter to quarter. So what is the growth rate from 39 to 42, from 42 to 103, and so on. And since we know that averaging growth rates, we afterwards have to calculate the average of the geometric average of the growth factors. I will calculate here the growth factors. Let's put in then here another line. So I write down here growth factors as a time series, and the growth factors is just the following value by the former value divided by 39 and taking this until the last quarter, and these are now all our growth factors, and we have to calculate the average growth factor, and this is just the geometric mean equals the geometric mean of all our growth factors and let's take this also in red, and then we have to apply this average growth factor in order to obtain our forecast. So we then calculate 659 times 1.207. So an increase of the last value of roughly 20% equals 659 times 1.207 is then our forecast. And this also in red. So average growth rate, then calculate the average growth factor. This is roughly 1.207, I think. 1.207, and multiply the last data point with the average growth factor. So we obtain y hat 2023 Q1 is roughly 1207 times 659 is roughly 795.7. 795.7. 7. And we should also do it for the annual case. Let's do this, that I have a little more space. Like this, and insert 1. So annual data. So for annual data, we then have 2019, 20 until 22, 19, oops, and the forecast, of course, will be then for 23. And therefore we have to calculate the average revenue for every year. So this will be the average of this P3 until P6. And then we have to change P7 to P10 and P11 until P14. Here on the left, you see that you compute the right data. And the last one, P15 to P18. Oops. Again. Oh, yes, I've skipped them. We calculate the growth factors. This equals this over this. And the geometric mean of the growth factors. Oops. And then we obtain as a forecast 571.5 times 2. So this would be the forecast for the whole. And well, we want also to have a forecast for 2023 Q1. And for this, we then calculate in every year the part of every quarter. So this I will do in a new sheet. Then let's just cut there. So what we need is the sum of our revenue, oops, course the sum. So total revenue of our 4 years. And then we want to calculate always how much percentage is 39 of the total revenue of the year, 282. So we calculate this one is 39 over 282 and F4 with the two dollar signs, and this one we have to do for all 4 years, but of course in this case we have C6, but this has to be C10. So 6 we have to replace by 10. And in this case we have, oops, this is right, 10, yes. And here we have to replace 6 by 14. Hopefully this is right now. Yep. And this also. And in the last case, 6 by 18. Let's format this in percentage. And then we have we should calculate now the average of every proportion in every year. So what do we have to do then is for Q1 we obtain 1 over 4 times this plus this plus this plus this, and oops, what's wrong? Nothing, I think I forgot a bracket or something like this. So this works. Oh, here I have Q4. This is wrong. So this is then 3, 7, 11, and 15. Now I have the right series, and this of course I can just copy downwards, because if I copy this, the cells just move one line below, and here we see that this is okay. Okay, so these are now our averages, and these averages we have our forecast for 23 of 1148, and this forecast we take, and now we say that the forecast for 2023 Q1 will be 17% of our total forecast of total revenue in 2023. So this will be then 17% times 1181, 1141. And well, also this was not asked. Let's do it for the whole year and all quarters. And this one for, well, downwards. And not percent, but this one. And then we have our forecast of 198. So average growth rate annually, we obtain the growth factor as 2, roughly 2, and then y hat 2023 is roughly 148, and average proportion for Q1 equals roughly, this was 73%. So y hat 2023 Q1 would be roughly 198.9. 198.9. And the last one, the linear regression. And for this, I show you a new method. Of course, you can calculate the linear regression via the formulas I have given to you, or what you also can use is the option, oops, Hello? Uh, Hello? Do you still hear me? No, it's back. I don't know what happened to my computer. Something weird happened. Now I'm back in business. Okay. So what you still hear me? Can you give me a feedback? Because my monitor just stopped working. Okay, thank you. So, you have the option in Excel, if you plot your data, that you just click on your time series, and then you have here the trend option, and that you can see it. I have to move it to the right, and then you can choose what you want, and here you have linear regression. And for the linear regression, you can also choose that you want to see the estimated parameters for the regression and also the coefficient of determination. And this we want to put in, and then you see here your linear regression line. And using this, then we have for the linear regression for the 3.75 minus 21.25, and let's take these numbers. Linear regression would be this one, and then of course we just insert for our forecast that we can say, well, we put for the next data point, how many data points do we have? I think 4 years, so 4 quarters, so we have 16 data points, 2019 to 2020. So we have 16 data points. Oops. And so our forecast for the next one, 2023 Q1, would be the 17th data point. So 2023 Q1 would be the 17th data point. So our forecast y hat 2023 Q1 would be then 43.7.5 times 17 minus 21.25. 5, and this is roughly, this I have to do by hand. So here then linear regression is 2023 Q1 would be equals 43.75 times 17 minus 21.75, and this is 765. Am I right? 25 here, sorry, 25. So 722.8. 722.8. Yeah, and well, if we all compare these values here, that you see that we have really large differences in forecasting. And well, in the end, it's up to you, and this is then the task of a good forecaster to choose the relevant method in order to obtain a reasonable forecast. And yeah, it's also always good thing not only to choose one method, but comparing these methods. Well, since we are already 9:15, we will skip this question here and moving to the next one. But so in the housing markets, we have an agent selling 26 flats, and he is calculating a covariance of 5,760, standard deviation of 223, and here a standard deviation of 21.9, and the average of 1,100 and average of 80. Calculate the linear regression line. Hopefully I have the formula here for linear regression. Oops, because this is this one here. So we have covariance is over variance of x is just b. So a b is covariance of xy over x. So variance. So we have then to keep in mind that G should be X and the rental should be Y. So we obtain 5762. This is the standard deviation. So we have to square 223.61 is roughly B equals 576 over, what did we have? 223.61. 223.61 squared is 0.12 roughly, or roughly squared 0.11, and this was 5. And for A, what do we have? Y bar minus BX bar. Oops. Here. A is Y bar minus BX bar. And we just insert Y bar is 1100 minus B 0.115 times 80. So A equals 1 minus this times 80 is then roughly 1000. And what do we have? 90.8. 90.8. So B, what is the marginal price? Per square meter. Well, there, of course, you just have a parameter B, because if you have a linear function, then of course the first derivative is just the slope of this linear function. And C, estimating 100, a flat of 100 square meters would be then just y hat is A plus bx, and inserting we have then m of 100 equals 190.8 plus 0.115 times 100, and this will be equals A plus 100 times this, and then oh, I did something wrong here. What is my mistake? I chose the standard deviation of y, and I have to choose the standard deviation of x. So that you know this, let's use this one has to be 21.9 squared. So we obtain 139.2, 139.2, and then this is 12, sorry. This is roughly 12, and 1340, and this is wrong, and this is wrong. 1340 times 12, and then of course no, this is 139 we have here, sorry. Up. 139, 139, and this is then roughly 1340. Well, again, you should do what you are doing. You should know what you are doing. And yeah, to obtain just more or less the same rental for a flat, which is 20 square meters larger, this is not a very reasonable result, and this is much more reasonable that compared to the average we have yeah, much more expensive flat. Okay, what else do we have? Next one. Three. Now at first, this one. And this one. So we should also calculate the linear regression and interpreting the parameters and the correlation, and we should also estimate. So then we also take our data, put it into our Excel file, and we have this would be output, the first one, output, and this would be costs. Well, in this case, if you remember, we could calculate all this via where do we have it? These formulas here. So calculating A via this and B via this formula. But of course, we can also directly feed in our data in a diagram. But since we want to have that output is depending on costs, I just change these two columns. Up. And then we have here X and here Y, and plotting the data. And then again, we can calculating the trend. And putting in our numbers. And this would be then our regression. And what should we do? Oh, sorry, we should do it the other way around. Costs depending on output, of course. So just a step back. So again, we do it the other way around. And this should be X and Y. Sorry. So this would be our regression line. Up, up, up. This one. 20. And interpret the parameters. Well, this would be fixed costs, and this would be variable costs, as you know from your business administration courses. And this correlation is, of course, then the square root of r squared. Let's calculate this one is then square root of 0.72. 0.872. 0.933. And estimate for 1,100 hectoliters would be y of 1,100 equals 1.8652 plus 3,500.3 times 1,100. So y of 1,100 equals 5.8652 times 1,100 plus 3,500.3 is roughly 9,952. And the last exercise is here. So we have within a company a multiple linear regression, and we obtained this data and interpret the coefficients. Well, if xu increases by 1 unit, y increases by 0.047, and if x2 increases by 1 unit, y increases by 0.0. 1, 2. So in general, this linear regression, as always, gives us a hint what is the marginal increase of the dependent variable due to an increase of our independent variables. Marginal increase of y depending on x1 or x2. Well, interpreting this coefficient beta 0 can hardly be interpreted because why? Well, we have here our logistic costs depending on revenue and orders, and this would mean if we do nothing we would have minus 2.77, and this is economic nonsense, more or less. And this you have quite often, that the coefficient beta 0, you have to keep in mind that quite often this cannot be interpreted in an economic way, since beta 0 is smaller than 0. The coefficient of determination, there of course we have of b, which costs do we expect? Then just we have to insert 400,000 and 45, and for this of course we have minus 2.77 plus 0.047 times 400,000 plus 0.012 times 4,500. Well, this you can just insert and calculate by your own. And the coefficient of determination, well, we have here the total squared deviation from average, and here we have the deviation of the true data points with respect to the estimated data points, and thus we obtain r squared equals 3082 minus 477 divided by the total squared deviation 824, and in the end is the assumed linear dependence, since we have made here a linear regression significant to a level of 5%, and for this we have to do an f-test, and let's see, our f value was, where we are, f-test, here we have our f value, So let's calculate r squared. R squared equals 3824 minus 477 divided by 3824. Oops. Quality sign 0.875. Up. Ah, There's my pen. This is 0.875. And what is n? We have over the last 23 months. So n is 23. And how many parameters do we have? We have two independent variables, x1 and x2. So k is 2, and then we have f in our case is 0.875 over 2 divided by 1 minus 8.75 divided by 23 minus 2 minus 1. And then we have the empirical value of f equals f emp equals this over 2 over 1 minus r over 23 minus 2 minus 1. Oh, sorry. I have to move in here. 23 minus 2 minus 1 is 20. And then I have to choose here all the right brackets. Hopefully this will work. Up. No. So d5 divided by, no, this has to be c5. Now it works. So we have roughly 70 for f empirical, and we have that this is distributed due to 2 and 20, and we should test on 5%. And for this I gave you the following tables. Please give me another 5 minutes. 5%. So we take this table 2 and oops, 20. This is missing. What is then the value of f? Oops, This is 0.95 to 20, hopefully. So our theoretical value is roughly 2.5. F theoretical is roughly 3.5. This is F 95% of 2 and 20, and then 70 is larger than 3.5 because in our distribution f of x, we have here our critical value, maybe 3.5, and 70 is somewhere here. So we are in this tail that our null hypothesis that we do not have a linear dependence is rejected. Then H0 beta 0 equals beta 1 equals beta 2 equals 0 is rejected. And the last exercise is our t-value. For a level of 1%, E is the t-test, and for this we have to choose, oops, where is it? This one. And there I told you that we always do only the two-sided tests. We only use two-sided tests. So in our case, beta m will be always 0. So our t beta hat will be always beta m hat over the standard error of our regression parameter, and we should do it for beta 1. So it is 0.047 divided by standard error 0.01267, and this is then roughly, this was F0. And then we have T-amp equals 0.047 divided by 0.01267 is 379. And we have this, that this is distributed Tn minus k minus 1. N is again 23, 2 and 1. So we have T of 20, two-sided, alpha equals 1%, so we have to look at 99.5%. So hopefully I gave you this in the table. This is the F value, and no, also I need here a 20. So then let's calculate this here with the t distribution of 0.95 and 20. So the theoretical would be 2.84. Here, this is roughly 3.7. This would be 2.84, and then we are here, and this is 0.5%. This is 0.5%. This is the critical value with 2.84, but we are at 3.7. So H0, the null hypothesis, beta 1 equals 0 is rejected. Ooh, it took a bit longer than I forecasted, I'm sorry. So then let's at first stop the video.